Today's lesson is on infinite series. Recall that an infinite series is a series, which means we're adding everything up, that continues without end. So you'll often see the dot, dot, dot at the end of it. Let me get a small pen here. For the sum of a series, so a series with n terms, a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. As n approaches infinity, so it means we're using millions and billions and trillions, infinite terms, it goes forever, then the sum to infinity would be, so notice now that the subscript is infinity, a sub 1 plus a sub 2 plus a sub 3 plus dot, 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 meaning that it goes without end. So we're going to look at two different things. We're going to look at increasing series, and we're going to look at decreasing series down here. First, increasing series. As we add the terms that get bigger, so the increasing series means the terms are getting bigger and bigger and bigger. They're actually getting farther and farther and farther from zero. Then the sum would be getting bigger and bigger and bigger, also farther from zero. So the sum is increasing to infinity. If it's going in the negative direction from zero, then it's decreasing to negative infinity. Either way, we say that that sum has no limit. So let's look at some of those. First, arithmetic series. So for the two arithmetic series, it says whether d, that common difference, is positive or negative or a fraction. Arithmetic series will have no limits. Because no matter what, you're always adding on that d value, regardless of what it is. In this first case, the d, the common difference, is 4 minus 8, so that common difference is negative 4. And we would have to add up 8, 4, 0, negative 4, negative 8, negative 12, negative 16, negative 20, etc. What you can see happening here is these negatives are getting farther and farther from zero. And so we're going to keep tacking on bigger and bigger negatives. And so this sum has no limit. And it's actually decreasing to negative infinity. It's going to negative infinity, but that's the same as no limit. For the second example, we can see the d value. Let's see, 3 halves minus 1 is a half. So the common difference between terms is a half. So the next few terms would be 8 halves, 9 halves, 10 halves, 11 halves, etc. So we're adding on 4 and 4 and a half and 5 and 5 and a half and 6, and we just keep adding and adding and adding. If we're adding and adding and adding, then there really is no limit here. And this one, the d value is positive, and so we're summing toward positive infinity. All right, how about still increasing series, but geometric? So of course, geometric series, we have our ratio value. In this first example, the ratio is 2 divided by 1, so it's 2. So we're going to be doubling our numbers each time. We'd be adding on 64, then 128, then 256, etc. So obviously these numbers are getting very, very big. When you're adding on bigger and bigger and bigger, you have no limit. So the sum has no limit. And we are adding on bigger and bigger and bigger, so it's going to positive infinity. If I could keep going and keep adding on larger and larger numbers that are doubling, I would have no limit. So that occurs when r is greater than 1. It says the absolute value because, of course, it could be negative. And in this case, this 2 value is greater than 1. But a much cooler thing happens, and we're still in geometric series down here, so I'm going to sort of just kind of point. We're still in geometric series right here. But now we're switching over to if the series is decreasing. So if the series is decreasing and we start adding smaller and smaller terms, then that sum does something cool. It gets closer and closer to some special value. And it's a value we can figure out, some special value. And then we say that is the limit of the sum, that special value. So this only happens for geometric series. Notice we're not doing the arithmetic here because we did it up above. With arithmetic, there's never a limit. So in this case, if the R value is less than 1, the absolute value of the R value is less than 1, that means we're looking at a fraction between -1 and 1. So we're looking at a fraction. Then the series is going to approach that special value. Here it is. This is still the special value. We're going to experiment with them a little bit, but basically, there's a formula for this. And the formula for this is that the sum of the infinite series, you see the infinity symbol here, equals the first term in the series, a sub 1, over 1 minus the R value. So R is the common ratio, of course, that you can find by dividing the second term by the first term. So let's take a look at this example here. It says for the geometric series below, find the sum of the first 8 terms and the first, I'm going to switch this to 12 terms. And you'll see why in a second. And then it says, can you figure out, after that, we're going to find the sum of the first 8 terms, and then we're going to find the sum of the first 12 terms. And it says, after that, can you figure out what that special value is? Here's that special value again. If we could keep adding on and adding on and adding on. So let's use our formula for the sum of a geometric series. And that, remember, it's given to you on your formula sheet. It's the first term, a sub 1, times 1 minus r to the nth power, all over 1 minus r. So we need some information here. For this series, a sub 1 is 5, the first term. And the common ratio is nice and easy. I can do 1 divided by 5, 1 divided by 5. So that's nice. So filling these in for the first 8 terms, the sum of the first 8 terms would be 5 times 1 minus 1/5 to the 8th over 1 minus 1/5. Let's make sure you do all that well. I'm going to put this into the calculator. All right. So we have 5 times 1 minus, the board is not reacting very well, 1 minus, and I'm going to put this fraction in parentheses, 1/5, I could have used 0.2, to the 8th power, okay, there we go. Oops, that's my numerator. All right, there we go. I'm going to hit enter, that's my numerator. Divided by, and my denominator is, in parentheses, 1 minus 1/5. I can do it like this because of order of operations. 6.249984. first 12 terms. So in other words, if I could keep going here and get all these terms and write down 12 of them and add them up, what would they be? So again, the first term is 5. 1 minus 1/5 to the 12th power. Okay, all over 1 minus 1/5. I would have used 0.2 here, but let's go ahead and try this one on the calculator as well. All right, so I'm going to go right up here. One more. And steal that. And just go change the exponent to 12. Okay. So there's my numerator. 5 times 1 minus 1/5 all to the 12th. And that is going to be divided by 1 minus 1/5. And we should get another number that's real similar to the last one. We went from 8 terms to 12 terms. You see 6.24, and then 5 9s and a 7 4. 6.24, 1, 2, 3, 4, 5, 7, 4. So if we add up the first 8 terms, we get this. If we add up the first 12 terms, we get this. What do you think the sum would be for the infinite series if we could keep adding on these smaller and smaller and smaller fractions? Any guesses? Well, it's 6.25. See how close this is getting to 6.25. So we're actually going to use the formula to get that. So now if I actually just said, I'm going to use this formula to find the sum of the infinite series, then it would be a sub 1, which we know is 5. This is very valuable info, over 1 minus 1/5. And if you do that, I'll do it by hand, that's 5 over 4/5, right? Which is 5 times 5/4, which is 25/4, which is 6.25. So indeed we have the same value. Let's try another example here. This first one, well, first it says write in sigma notation. We can do that. And then second, determine if the sum increases without limit, decreases without limit, or approaches a finite limit. So let's see. We have to identify them first as geometric or arithmetic, because we know the arithmetics have no limit. So this first one, the first term is 1, and then I have a 3rd and a 9th. Can you tell? It's geometric, and the R value is, what am I multiplying by to get from term to term? 1/3. So that's definitely geometric, and we'll have to work with that one. Number 2, 2, 4, 6, 8. It's arithmetic. So we know the sum, look, the numbers are getting bigger and bigger and bigger. If we go to infinity, then we have no limit, and it's definitely increasing. Number 3, let's see, 5 to 1 would be subtracting 4, subtracting 4, subtracting 4, yep. Arithmetic. The D value is -4. I didn't put the D value here. D value is +2. So this one's going to have no limit, and because we're continually adding on a negative, it's going to be decreasing farther and farther away from 0. No limit, decreasing, no limit, increasing. All right, So back to this first one, it's arithmetic, or I'm sorry, back to this first one, I'm reading off my page. It's geometric, the R value is less than 1, so we know it would be a series that is decreasing. So we can find the sum of this infinite series using our formula, a sub 1 over 1 minus r, and we have 1 over 1 minus 1/3, just using these two values here. So that's 1 divided by 2/3, which is 3/2. Part A says to write this in sigma notation, so I'll do that as well. The sigma is the sum as these terms go from the first term to infinity, and then we just have to figure out the any term expression, and that's the r value here. It's a times the r value to the I minus 1. So if we did the any term expression for a geometric, we would say it's a sub 1 times r to the n minus 1. Well, in this case, a sub 1 is 1, and r is 1/3, and n minus 1 would be my exponent. So that's how I got that. All right. Now at the end here, we look at something that we're maybe more familiar with, but we can relate it to this topic of the infinite geometric sequence. So the first examples, these are infinite repeating decimals. We know these. If we say 0.3 repeating, it's really the same as that, 0.3333 dot dot dot. When we chop this up, this is 0.3 plus 0.03 plus 0.003, right? Dot dot dot, and that's what I have here. So it is actually an infinite geometric sequence, and the terms are decreasing. Infinite decreasing geometric sequence. The first term is 0.3. The r value, let's take the second term divided by the first term, so the r value is 0.1. And so the sum of this infinite geometric decreasing sequence, the sum of all these decimals would be a sub 1 over 1 minus r. So we have 0.3 over 1 minus 0.1, or 0.3 over 0.9. And if you need to use your calculator, go ahead. I'm just going to move these decimals out. I get 3/9, and that becomes 1/3. You should recognize that 1/3 is 0.333333 repeating. So it's kind of cool. We can use the formula for the infinite geometric decreasing sequence to express repeating decimals as fractions. The second one, so this has two digits repeating, So I would write this one out as 0.12 plus now I gotta fill two spaces with zeros, 0.0012. Now I have to fill four spaces with 0, 0, 0, 0, 0, 1, 2, etc., and then six spaces, so that it bumps over two spots every time. So let's do our a sub 1 again. The first term is 0.12, 1200ths. The r value is, let's take our second term divided by our first term. So the r value comes out to be 1/100th. And so we can find the sum of the infinite sequence by our formula. which is 4 over 33. So we know as a fraction, we can even try that. 4 divided by 33 is 0.12121212, repeating. All right, last but not least, we're revisiting our old friend E. Remember, E is that special number that we used in logarithms, and we used it in the exponents chapter. On your calculator, you can hit your second button and find e to the x above ln, and then put a 1 in as its exponent. 1 is going in as its exponent. And you'll see that the value of e, which is e to the first, is 2.71828, 1828. It actually keeps going. It's an infinite decimal, doesn't repeat or terminate. Well, e has a special infinite sum that it is associated with. However, just so you know, it is an infinite sum. It is decreasing, but it is not geometric. So you cannot use that formula up above. But basically what it is 1 over n factorial, as n starts at 0. 1 factorial, 2 factorial, 3 factorial, etc. Just do a couple more. And then we keep going with that pattern with the factorials in the denominator. And if we took all these and added them up, 1, and remember 0 factorial is 1. That would be 1 over 1 plus 1 over 1 plus a half plus 3 factorial is 6. 4 factorial is 24. 5 factorial is 120. 6 factorial is 720. If we started adding up all these fractions together, here's your 2 right here, then your fractions start adding on, they get smaller and smaller and smaller, so we end up with 2.718281828, yada, 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 yada. So it's just kind of cool, a little extra thing there. It is not geometric though, there is no common ratio, so we can't use that formula up above. Okay? This is the last chapter, I believe, of the year. Last chapter, last lesson, everything. That's not a very attractive smiley face. There we go. There you go. So we'll see you in class tomorrow. Congrats, you made it.